You've seen it, right? AI can whip up incredible art from just a few words. It can write code in the blink of an eye, and it can even chat with you in a way that feels, well, almost human. But how on earth does it actually work? Is it really thinking, or is it just the world's best mimic? That's the puzzle we're going to unpack today.
And this right here is the question that gets to the heart of it all. This isn't just about cool tech, it's about what intelligence even is. So to even try and answer that, we've got to pull back the curtain and see how a machine actually, well, learns.
So, where do we even begin? Well, it actually helps to start with something we all know pretty well, our own brains. Believe it or not, the most popular AI models out there today are directly inspired by the way our own neurons are all wired up.
Okay, so take a look at this. It's kind of wild how closely these things line up. In our world, a stimulus, like, say, seeing a ball flying at your face, becomes the digital input. Our receptors, our eyes, become the AI's input layer. A neuron firing in your brain is basically a processing element in the machine. And finally, your response, actually catching the ball, is the machine's output. It's this almost one-to-one translation from biology into code.
All right, so the structure is kind of similar. But what about the learning part? Well, get this, the parallels don't stop there. It turns out machines learn a lot like we do, by messing up. They learn from experience, and more specifically, from their mistakes. When you boil it all down, machine learning is really about one thing: experience. You just feed a machine a truly mind-boggling amount of past data, and its whole job is to become an expert on that data's patterns. And why? So it can get so good at understanding the past that it can basically predict the future. Right, but how does a machine even know it made a mistake? I mean, you can't learn if you don't know you're wrong, right? Well, for an AI, that's where something called a loss function comes in. It's basically just a piece of math that calculates, okay, how wrong was I? It's the AI's big oops moment. It's uh-oh calculation.
So the AI knows it's wrong. Now what? It has to get better, and that's where a cool idea called gradient descent comes into play. The best way to think about it is like this. Imagine you're on a hill, but it's super foggy. You can't see the bottom, but you want to get there. What do? You feel around with your foot and take a small step in whichever direction is steepest downhill, right? That's exactly what this is. The AI makes these tiny adjustments again and again to get that error score lower and lower.
So this whole learning thing really boils down to two main steps. First up is training. This is where the machine just pores over all that data, using that loss function and gradient descent to build its understanding. But then comes the real test. You give it brand new data, stuff it has never, ever seen before. And that's the moment of truth. That's what separates real learning from just, memorizing the answers. And what you get from this whole process, this training, this testing, is a machine that is absolutely, unbelievably good at one thing: finding patterns. And that really is the superpower of AI today. We're talking about sifting through oceans of data, text, pictures, stock market trends, you name it, in a way no human ever could. It sees these tiny little connections, these hidden rhythms that we would completely miss. It is, hands down, the ultimate pattern matching machine. But, and this is a huge but, here's where things get really interesting. See, being a master at matching patterns is not the same thing as actually understanding why those patterns are there in the first place. And this is the exact spot where that nice, clean analogy to the human brain just completely falls apart. Yeah, this quote from a researcher, David Maiolo, just hits the nail on the head. This process should not be mistaken for reasoning. And that's it. Everything we've talked about so far, the learning, the correcting, the predicting, it's amazing, for sure. But it isn't reasoning. It's more like a really convincing imitation of intelligence, not the real deal. So let's break this down, because it's really the key to everything. On one hand, you have pattern recognition. That's what AI is a rock star at. It finds connections in data it's already seen. On the other hand, you have logical reasoning. That's the human advantage. It's about using basic rules of logic, cause and effect, to figure out something totally new. For example, an AI can learn that pictures of dark clouds usually lead to pictures of rain, but it has zero understanding of physics, of evaporation, of why clouds actually make rain. Okay, so if the AI isn't actually using logic, then how in the world is it so good at this? How does it even know where to start looking for all these patterns? Well, the secret is, it kind of cheats. It gets a little head start. This head start has a technical name: inductive bias. But you can just think of it as a set of shortcuts or built-in assumptions that the programmers give the model. Like, for a language AI, a common bias is the idea that words that are close together in a sentence are probably more related. The AI doesn't learn that rule, it's just baked into its design from day one to help it get going.
And check this out, because this visual really shows you how important that is. Imagine the AI has to find the right answer to a problem. Without any help, it's searching in this massive area called the hypothesis space. That's the whole big circle. All the possible solutions are in there. But the correct answers, they're just in that tiny little purple spot. Trying to find that without any guidance, it's basically impossible. It's like looking for one specific grain of sand on every beach on Earth.
But now, watch what happens when you add a good inductive bias. That search area, the big circle, gets way, way smaller. The AI is essentially being told, hey, don't even worry about all that other junk, just look over here. And suddenly, finding that little purple spot goes from being impossible to totally doable.
And listen, this isn't just some nerdy academic debate. This gap between pattern matching and actual reasoning has massive, real-world consequences. Think about a self-driving car. It needs to do more than just recognize the pattern of a child running into the street. It has to reason about physics, about stopping distances, to make a split-second life-or-death choice. And it's the same for AI in government or managing global supply chains. In these high-stakes games, you absolutely need a system that gets the why, not just the what.
So at the end of the day, here's where we stand. We've built these absolutely incredible machines that are masters of finding patterns in the past. But the next giant leap, the true future of AI, is all about teaching them to understand the why. So the question we're left with is, how do we build a machine that doesn't just mimic the past, but can actually reason its way through a future it's never seen? That right there is the next great puzzle to solve.
Welcome to The Explainer. Today we're diving into the source material on a really huge and honestly super important topic in the world of artificial intelligence, machine learning bias. So let's just jump right in with a big question. Think about it. We're at a point where AI is already making these kinds of high-stakes decisions about our lives. This isn't some science fiction future. It's happening right now. And that makes the risk of an algorithm being unfair, well, it makes it incredibly personal. That's why getting a handle on bias is so important.
All right, first things first. To really get a grip on this, we've got to ask, what exactly is this ghost in the machine that we're talking about?
Okay, so what does that actually mean in plain English? The key word here is systematically. This isn't about a one-off glitch or a random mistake. We're talking about a built-in problem that consistently and predictably produces unfair results. And our source material is really clear. This bias doesn't just appear out of nowhere. It comes from the flawed assumptions that we humans make when we build these things in the first place.
And this right here, this is probably the single most important idea to get your head around. An AI doesn't just wake up one day and decide to be unfair. Nope. It's a reflection of the world we show it. If the data we feed it is full of our own societal biases, well, the AI is going to learn those biases. Sometimes it can even make them worse. It's basically just a mirror.
Okay, so if the AI is learning this bias, where is it actually coming from? Let's peel back the layers and look at the exact spots where these errors can creep into the whole process.
This chart here really lays it out perfectly. You see, bias isn't one single point of failure. It's more like a leaky pipe. It can spring a leak at almost any point. It can start right at the beginning with the data we collect or the features we tell the machine are important. It can be in the algorithm itself or even in how we deploy and monitor the thing out in the real world. A problem in any one of these stages can mess up the entire outcome. And, more often than not, it all starts right here with the data. It is the foundation for everything. You've probably heard that old saying, garbage in, garbage out. Well, it's 1,000% true in machine learning. If you feed an algorithm biased data, you are absolutely going to get biased results. Simple as that. So let's get a little more specific. This table shows two huge ways this can go wrong right from the get-go. First, there's data bias. That's when the data you're using just isn't a good reflection of reality. The classic example is a hiring tool trained mostly on men. It's just not going to be very good at evaluating women. But then there's something a bit sneakier, feature bias. This is where you use a piece of information that seems totally harmless, like a zip code. But because of how our neighborhoods are structured, a zip code can actually be a stand-in for things like race or income, introducing a massive bias without you even realizing it. Okay, let's look at one really fascinating example of data bias, just to see how deep this rabbit hole goes. It's called survivorship bias, and it's basically what happens when we make the classic mistake of only studying the winners, the success stories, and we completely forget to look at all the ones that didn't make it. Here's a perfect example from our source material. Let's say you want to figure out the secret to a successful business. If you only study the companies that are thriving today, you're missing a huge piece of the puzzle, right? You have to study all the businesses that failed too. That's where some of the most important lessons are actually hidden. And this visual just makes it so painfully obvious. Look at that. When you only focus on the survivors, the picture you get of the world is totally warped. It's not reality. And if you train an algorithm on that incomplete, distorted picture, well, you can imagine the kind of bad decisions it's going to make. Okay, so we've seen how this bias gets baked into the system. The big question now is, what do we do about it? How do we get it out? Well, researchers have come up with what you can think of as a 3-part treatment plan. It really all comes down to when you decide to step in. You can try to fix the problem at the source by cleaning up the data before you even start training the model. That's called pre-processing. Or you can actually change the learning process itself, building fairness rules right into the algorithm during training. That's in-processing. Or finally, you can just take the biased results at the end and try to adjust them to be more fair after the fact. And that's post-processing. But, and this is a really, really big but, none of these are a perfect cure. Applying these fixes often comes with some serious side effects because there's a fundamental conflict at the heart of all of this. Just look at this number, 53%. That's a lot. One huge study found that in over half the cases they looked at, trying to fix the bias in a model actually made the model worse at its main job. And that's because when you force a model to be fair, you might actually be preventing it from using real, legitimate patterns in the data, which ultimately just makes it less accurate. And this gets us right to the core of the problem. It's this constant tug of war. On one hand, you want to improve fairness and protect certain groups. On the other hand, doing that can sometimes lower the model's overall performance. This creates a massive ethical and business dilemma. What's the right balance? How much accuracy are you willing to give up for more fairness? There's just no easy answer. So we've covered a lot of ground. What's the big takeaway from all this? What's the one thing you should really remember? Let's just boil it down to 3 key things. First, AI bias isn't a tech problem, it's a human problem. It starts with our data and our choices. Second, it's not one single mistake. It can creep in at pretty much any stage of the process. And finally, there's no magic wand to fix it. The tools we have often force us to make really tough choices between what's fair and what's accurate. And all of this leaves us with one final and absolutely critical question. This is not something that a bunch of data scientists can just solve with more math. Defining what fair even means is a messy, human, societal challenge. And as we hand over more and more of these huge decisions to algorithms, deciding who gets to answer that question, that's something that involves every single one of us.
You know, every single AI model you interact with, whether it's a chatbot or an image generator, is really powered by 2 fundamental phases, training and inference. In this explainer, we're going to break down exactly what they are and why the difference between them is just so crucial.
Okay, so at the heart of any AI project, you've got these 2 totally distinct phases, training and inference. And honestly, the best way to think about them is like this. Training is the marathon, and inference is a series of sprints. One is this long, grueling test of endurance, while the other is all about that explosive, lightning-fast speed.
All right, first things first, let's cover the basics. These 2 phases make up the entire life cycle of a machine learning model, from the moment it's created to how it's used every single day.
So training, think of it as the school phase. This is where data scientists feed a model just massive amounts of data, letting it slowly learn and adjust until it can recognize patterns. It's a really intensive, repetitive process, and it's all designed to build this deep, foundational understanding of a specific task.
And then you have inference. This is when the model basically graduates and gets a job. It gets deployed into a live environment, like a chatbot or a recommendation engine, and it starts applying all that knowledge to new data it's never seen before. This is the moment the AI actually starts generating results and providing real value.
Now, let's zoom in on the marathon of training. This part of the journey, well, it's all about raw power and pure endurance.
During training, the goal is pretty straightforward. You want to maximize throughput. That just means you're trying to process as much data as you possibly can, as fast as you can. It's an incredibly demanding process that can take days, sometimes even weeks for the really big models. So this incredible demand for resources has led to some much smarter training techniques. One of the most popular is called fine-tuning. Instead of building a giant model from square one, you take a pre-trained one and just kind of tweak it for your specific task. And a super efficient way to do that is called PEFT, or Parameter Efficient Fine-Tuning, which only adjusts a tiny, tiny fraction of the model.
Now check this out, because this slide shows the fascinating trade-off that these PEF methods give you. Just look at the numbers. LoRa gets you that top-tier performance, no question. But then look at LN tuning. It gets incredibly close performance-wise while using over 50 times fewer trainable parameters. I mean, that's a total game changer. It means you can get almost the same result with way less computing power, time, and money. It makes powerful AI accessible to so many more people.
And this diagram just brilliantly illustrates the whole ecosystem that's growing around these techniques. We're seeing frameworks like this one, PEFT Factory, pop up, and they provide tools and benchmarks to make this kind of efficient training more accessible for everyone, not just the giant tech companies.
Okay, let's move on to the other side of the lifecycle, those quick sprints of inference. This is where the model is no longer learning, it's performing. It's showtime.
Once a model is deployed and out in the wild, the priority does a complete 180. It's not about raw power anymore. It's all about speed and efficiency. The goal now is to minimize latency because, there's often a real person on the other end waiting for an answer. Every millisecond counts.
And this is where a whole different crew takes over. Data engineers, IT specialists, their focus completely shifts. They're not training the model, they're integrating it into a live system. They have to manage the flow of real-time data, make sure it's formatted just right for the model, and then translate whatever the model spits out back into something a human can actually understand.
So these completely different goals, the marathon of training and the sprints of inference, they lead to a really crucial practical decision about the tools you need for the job.
Because choosing the right GPU for each phase isn't just some minor technical detail. It directly hits your project's cost, its speed, its overall performance. Seriously, using the wrong tool for the job can be incredibly wasteful.
For the training marathon, you need the most powerful GPU you can get your hands on, with tons and tons of VRAM. That's the GPU's dedicated memory to hold these huge models and datasets. But for the inference sprints, you pick a much more modest GPU that's just fast enough. It's all about that balance between speed and cost efficiency.
This quote from RunPod just perfectly captures the core difference in philosophy here. It's not about which GPU is better overall, but which one is better for the specific race you're running at that exact moment.
So let's bring this all home. Why is understanding this distinction, this duality between training and inference so critical for anyone working with AI today?
So here are the key things to walk away with. Training and inference are just different phases with totally different goals. Training is that marathon, focused on raw power and memory to learn from huge datasets. Inference is the sprint, prioritizing low latency and cost efficiency to get fast results to users. If you get that, it lets you choose the right hardware for each job, which optimizes both your performance and your budget.
And all of this leaves us with a final thought on the future of building and deploying AI. As these models continue to grow exponentially, getting bigger and more complex by the day, thinking about training and inference as two distinct specialized tasks, well, it might not just be the smart way to do things, it might be the only way we can keep up.